All right, hello everyone. So here we are back with some fun elevator problems. We have three different elevators. The first elevator is accelerating upwards at 2 meters per second per second. The second one is going at a constant velocity, so it's not accelerating. So the acceleration, the net acceleration, is 0 meters per second per second. And the third one on the right here is the net acceleration is negative 2 meters per second, so it's kind of slowing down. So I think we can kind of think of this as you get in the elevator and you press the button, and the elevator will first do, the first one for a couple seconds. So it'll accelerate up to its speed, and then it'll hold its speed as you go all the way up to maybe the 10th floor. And once you approach the tenth floor, the elevator is gonna go from the second elevator set to the third elevator set. And we're gonna kind of slow down as we get to the 10th floor, and then eventually stop. Right. So we're accelerating, not accelerating, decelerating, and then we're done. Negatively accelerating as opposed to decelerating. But those are really the same thing. Anyway, let's get into it. So this is really going to be an investigation of Newton's second law, also his third law, and we're going to talk about the sum of the forces and how the sum of the forces are going to be equal to the net acceleration and the mass, the product of those two things. All right, let's do it. So I think we can start by saying let's look at the first one. We have the acceleration due to gravity is negative 9.81 meters per second squared. That's acting on this person going in the downward direction, but the net acceleration of the whole entity in particular, maybe this is blue, going downwards, this is acceleration due to gravity, but the entire thing is moving upwards at 2 meters per second. So there must be kind of this normal force that's pushing that body and resisting that negative 9.81 meters per second motion. And we'll put it in white, and we're going to say maybe it's this motion, right? So that the sum of the blue and the white vectors are going to equal that orange vector, right? So another way of writing this is saying the sum of the net forces, is equal to the mass times the net acceleration. And in this case, we'll call our mass 10 kilograms. Got some tiny people. We have maybe some children, right? And then our net acceleration is 2 meters per second, so that's equal to 20 newtons, and that's the net force that's going upwards. So again, that's the orange. So if 20 newtons is our net force, well, the net force is the sum of the net force. All of the forces acting on this object are going to be the acceleration due to gravity plus the the normal force, but the acceleration due to gravity. So we'll say F equals ma. The acceleration due to gravity in terms of the mass is not 9.81 meters per second. It's actually 9.8 is the acceleration times the mass of 10, so it's actually 98, negative 98 newtons, and that's the force of the force of gravity acting on the mass, which we call the weight. So the F sub W, we'll call that negative 98, and we'll add the force, F, we'll call it normal, the normal force, which is, again, the white thing that's pushing up and resulting in the net acceleration upwards. Otherwise, we'd be accelerating downwards, which we're not. With the system in general, will be accelerating upwards, which it is not. So we can find the normal force, which is the force that is kind of pushing up on you, or this force that the scale is reading, which is 118 newtons. You take 20 and you add 98, you get 118 newtons. Sweet, let's erase. And move on. Good. Okay, now now we have problem number 2 here. We're not accelerating, so the sum of the forces, that's a bad sigma. The sum of the forces, I'm going to call it net forces, is going to be mass times acceleration, net acceleration. And so the sum of the forces is actually going to be equal to 10, and the net acceleration is 0, so the net forces are going to be 0. I hope that makes sense. 0 times 0. So the sum of the net forces is 0, so we have 0 is the net forces, and the sum of those forces is the weight, or the force due to gravity that's acting on the mass. So force equals mass times acceleration due to gravity, that's for weight. We're going to add that to the force, the normal force, normal. So F normal when we're at constant velocity, so 0 acceleration, is a positive 98 newtons. All right, and now we have our third and final elevator problem. Now we're accelerating downward as a whole, right? So now we're accelerating downward as a whole. We have, actually I think I did that in orange. I'll do that in orange again. So that's our net acceleration. We have our gravity, which is acting like that. We have some net force maybe going this way, which is the normal force that's making us not fall through the floor. Awesome. So, mine white? Yes, mine white. Okay, good. So we have, again, we'll do Newton's second law. It says the sum of the net forces is equal to the mass times the net acceleration. I suppose I could write that better. The net acceleration, so the sum of the net forces is equal to the mass, which is 10, times the net acceleration, which is negative 2, so that's negative 20 newtons. So negative 20 newtons is equal to the sum of the forces. The sum of the forces, or the two forces that are acting in the vertical direction on this object, is again our negative 98 newtons, which is due to gravity, which is the weight, plus the normal force normal, and therefore we can add 98 to negative 20. So our normal force, again, this is kind of the force that the scale will be reading, is going to be 78 newtons. So we can take a step back and look at how this might make sense or not make sense. And we have example 1. The normal force, our scale, would read 118 newtons. I think that makes sense because if we're accelerating upwards, we're kind of being pushed into the floor as we accelerate. I think it makes sense that that normal force is actually going to be greater because it's not only overcoming gravity, but it's also overcoming the positive net acceleration that the elevator is experiencing. So those two forces should add together. So 20 plus 98 is equal to the normal force. I think that makes sense. So in the second one, we have kind of our net acceleration is 0. So the two force vectors, maybe have, your gravity is this way. What color was that one? I think white. Right, and then your normal force should be equal and opposite in the other direction, so you're not moving, or you're not accelerating, rather. Case 2 is actually a special case. We could say that we are essentially at rest, because it really depends on what our frame of reference is, right? If we're frame of reference with respect to ourselves, or if we're hurling through space, we might not have a frame of reference with which we can say we are moving at a constant velocity, and we really wouldn't feel it if we couldn't maybe see through the elevator. Anyway, yeah, so that's kind of an interesting caveat. Newton's laws say an object in motion will stay in motion, an object at rest will stay at rest. Essentially, that's what that's saying is if the object is not accelerating, it will keep doing what it's doing, right? So if it's not accelerating, it's either moving at a constant velocity or not moving at all, or moving at a constant velocity when the velocity is 0, meaning it's not moving. Interesting caveat. If that was confusing, just forget it, and it will not matter at all. Continuing on, we have the sum of the forces is equal to the mass, which is 10, times the net acceleration. Well, the net acceleration is 0, because we're not accelerating. So 0 is equal to gravity, so negative 98 newtons, plus a normal force, which should be equal, and opposite, which is positive 98 newtons. I think that makes sense. If we're not moving, the force of gravity, the weight, is going to be counteracted by the normal force, which makes sense. We have the third scenario here. We're saying it's going to be less than we would normally weigh. I think this also makes sense if we're free falling. We kind of have that gut feeling of our stomach dropping against us. I think that makes sense because we feel like we're lighter than we normally are when we're falling, um, maybe down the stairs or something. Um, and that is true because the force of gravity is acting with the net acceleration. So those two things are going to add together to get us something less than the force of gravity. Hope that made sense. Um, we can do some more fun, complicated ones with elevators, maybe like jumping in elevators and stuff like that. Elevators and free fall, all that kind of good stuff. Um, I hope that helped. Hope that made sense. And I'll see you in the next video.